Hello, this is the second video that I'm making in connection with quantum physics for the IB curriculum, and I'm going to be discussing the contribution that de Broglie made. Excuse my French pronunciation of that. And he was very influential because he thought of this idea basically under his hypothesis, where in the photoelectric effect, it was shown that waves can display both this particle and wave-like nature. And so what he thought, well, if waves can do it, what about particles? Particles can also display this, and he developed this formula, lambda is equal to h over p, and we will develop that formula also. This brings in the whole idea of the wave-particle duality and also matter waves, that matter particles have these wave-like properties. This over here is an experiment. We'll discuss this also, the experiment which verified de Broglie's hypothesis, and he also went further on to develop a formula for this. This is the one, and we will develop that formula also. So I hope you're going to find this useful. Now, firstly, going to the data booklet, we're going to use this formula, which is for the photoelectric effect, which basically gives the energy of a photon or a particle of light. Now, he used this formula along with E is equal to mc squared, which is the energy of a particle, or where that's something that has got mass. And he equated the two. He said, well, mc squared is equal to hf. mc squared is equal to hc over lambda. If we have c is equal to frequency times wavelength, and we just switch that formula around, and here we can see that our c cancels here, and we have one left there. mc, mass times speed, gives us p is equal to h over lambda, and this was de Broglie's formula that he developed for this. So his idea that something that has got momentum, something that has both mass and velocity, is equal to h and would have a wavelength associated with it. And we can actually work out the wavelength for any particle that has got mass also and velocity. Now, this has actually been verified that you can, and we'll look at that. But he went on to develop this formula over here. And in this he thought of, okay, these electrons behave like waves, so he viewed the electrons orbiting a nucleus as a standing wave. And in so doing, he used the basic formula that we have for a standing wave with closed ends. Lambda is equal to 2L over n, and we can see that where n is a natural number. And then taking p is equal to h over lambda, we can substitute this into there, this into lambda, and rearrange it slightly, and we're going to get that Pn is equal to nh over 2L. Now, these particles, these electrons, would have kinetic energy. Their energy would be in the form of a kinetic energy, a movement energy. And since Ek is equal to a half mv squared, we can rearrange that to m squared v squared over 2m, which is equal to p squared. M times v is p, so it's p squared over 2m. And then substituting this momentum in for that p, we get a formula En, because it's dependent on this natural number. And I'm going to put that in here, we're going to get n squared h squared over 4L squared, and then we're still left with the 2m here, 2m. And so finally we get, when we put that all together, we get n squared h squared over 8. It's this formula over 8m, because we're dealing with an electron, mel squared. And this is this formula over here. And it's basically looking at the electron as a standing wave around the nucleus. We have the n, which is a natural number, and so this leads to the quantization of the energy. As n is 1, it would be 1 squared is 1, n is 2 to become 4, and so forth. Now, de Broglie's hypothesis and his view that matter, electrons for instance, have a wavelength, was verified by a very important experiment. And I'd like to just talk about that for a moment. So we have in here outline an experiment to verify de Broglie's hypothesis. And it's this experiment over here, an experiment showing electrons, this one over here, that electrons are scattered off crystals of nickel and interfere with each other, also known as electron diffraction. Now, we can actually know certain things about the electron and then be able to verify it. And I'd just like to go through the mathematics of that. Now, if you get an electron and you put it between a potential difference, if this is negative, 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 and this is positive, 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 with a certain voltage, we know that the energy, that the E, is going to equal the voltage times the charge of the electron, VE. And that energy is given in kinetic energy. Now, we've already just proved that kinetic energy you can write for non-relativistic situations is p squared over 2m. Okay, but we also know that P, according to de Broglie's hypothesis, is equal to h over lambda. So if I put that into this equation, I'm going to get VE equals 8 squared. VE is equal to 8 squared over lambda squared, and we're still going to have a 2 and an m there. So if I take my lambda squared out, I'm going to get lambda squared is equal to 8 squared over 2VE and the mass of an electron, and we take the square root of that. Therefore, lambda is equal to h over the square root of 2VEm. Now, if we set it up in an experiment, all of these quantities are known. H is known, V is known because one knows that from the experimental setup. We know the charge of an electron and we know the mass of an electron. And so the wavelength, or the supposed wavelength of that electron, should be known. Now what they did was they shone it through a crystal, and by working with other light, they were able to work out the spacing in the crystal of nickel, and therefore able to predict the amount of diffraction that actually take place for that wavelength, and measure it. And they verified that this wavelength did actually fit in with the wavelength that was predicted or was gained from this experiment. And so de Broglie's hypothesis was verified. So that ends the discussion that I have on de Broglie and his contribution in quantum physics. Obviously it's very brief, and I encourage you to do a lot more reading and study into this aspect. Thank you very much.